All right, let's get started. Thanks again for joining us today. As always, we've got a good one for you this time. It's going to be different than what we normally do. Normally, we're talking energy code, HVAC. I thought I would chase down and try to find somebody that can talk about water heating because that is in the code, and we do have requirements for that as well. So I thought it'd be a good topic for us to get into. So we have the webinar title today, The Benefits of Demand-Controlled Recirculation Systems. As always, today's webinar is being recorded. It will be uploaded to YouTube, where you can find it by searching SPEAR on YouTube, or you can go directly to our website at eepartnership.org. Under the news section, you'll find it in our resources page. Once you're on our resources page, you'll see the link to our channel. We have well over 150 videos related to different topics, policy, legislation, energy code, of course, and just different types of topics that we have. Today's webinar is eligible for IECC CEUs. However, you must be present for at least 3/4 of the presentation to get credit. Within about 72 hours, you'll receive a course evaluation email from Kathy Lawrence. Please complete that survey and send it back to her to receive your course completion certificate. That will contain the title and course ID number you'll need when reporting your CEUs to IECC. Lastly, I'll have the chat feature open. Use that to report any technical difficulties or any questions you have. I'll also be monitoring the Q&A feature as well. So please put those in the Q&A section if you have a question. If it pertains to what we're talking about at that moment, we'll try to address the question as we go through. But by all means, if you have a question about something that is not related to what we're actively talking about and discussing, we can hold off to the end and go through it. Today we have Gabe from Innovative and Juliana from Innovative and AutoHot. So Gabe, I'll let you get started in just a second. Let me finish my last two slides here. So if anyone's on here that's new to SPEAR, what do we do, who we are? We're a nonprofit. We're one of 6 of the regional energy efficiency organizations throughout the country. We cover Texas and Oklahoma by advocating for the adoption and acceleration and enforcement of the energy code. We can help answer questions with energy code, ASHRAE 90.1. So we're kind of the technical assistants for SECO, the State Energy Conservation Office. So we're happy to help in any way that we can. We continually assist several cities with the adoption of 21 or the 18 to help them navigate through additional amendments to help kind of lessen the impact for your building community. My contact information will be at the end of this presentation, so please feel free to share that, and we can help with anybody that needs help with navigating through the energy code. So the last one I have on here is basically when we talk about energy code, I just put this up here. I'm not going to read all of it, but service water heating system is in the code. It does specifically talk about circulation and circulation pumps. So that's kind of why we asked these two to be on here today, to give us a presentation on the technology that's out there, what can be done to actually be compliant with code. Any of you building officials that are on there, is what we're looking for when you're talking about compliance to the energy code and the requirements that it has. So Gabe, I will stop sharing now and I will let you share your screen.
Thank you so much. I appreciate it. Thank you for the invitation, and thank you all for joining today. My name is Gabe. I'm with Innovative Manufacturing. We're the maker of AutoHot. It's a line of hot water control systems for different applications. Today, we're going to talk about demand-controlled recirculation, something that's very near and dear to me, and creating a high-performing hot water distribution system. So we're going to talk a little bit about just generally hot water distribution. We're going to talk about energy codes, and we're going to talk about some other hot water related topics. So the first thing I'd like to start off with is just to discuss, like, why is hot water important and how big is hot water? So hot water, as it turns out, is the first or second largest energy consumer of a residential house. It's roughly about 20% of the total energy pie. And every house on average uses about 50 to 60 gallons of hot water per day. And of that 50 to 60 gallons, about 20 to 23% of that water is wasted during the draw to get hot water. So, you know, as we're talking about hot water distribution, we're thinking about the magnitude of hot water. The other thing I want everyone to think about is what we call the water energy nexus. And maybe some of you have heard about this, maybe not, but it's basically the relationship between water and energy. And there's been a lot of research done, especially by the California Energy Commission, about the relationship between water and energy and how they're inextricably linked. So that's why I use this image of a chain, because even before the water is heated in your house, there is a ton of embedded energy in the water that we consume. So if you think about what the power it takes for the water to get treated to be, safe, potable water, and then, to get it, transferred from the source to where it's being used, requires a lot of energy. So, water systems in the U.S. consumed approximately 3% of the total annual electricity in the U.S. So that's kind of a big thing that, most times we don't think about, is that every drop of water has energy, latent energy that's embedded in it. And then also, on the flip side of that, it takes 2 gallons of water on average per kilowatt hour produced. So, in California, like none of the water that we drink comes from beneath our feet. It always gets, pumped over, several mountain ranges, 2,000 feet, 2,000 miles over mountain ranges. And so that energy required to move that water is pretty hefty. So, when we waste water, we're wasting energy as well. And I think the stat is something like, for every gallon of water that we waste, we're simultaneously wasting a kilowatt hour of electricity. What is hot water distribution? So when we're talking about hot water distribution, we're not really talking about the water heater and what type of water heater we have, whether it's a tank or tankless or heat pump. What we're talking about is the network of piping and fittings and fixtures and all the other components that work together as an interactive system to deliver hot water from the heating source to the points of use within a building. And so often we don't do this right. We don't do this efficiently. And as a result, water and energy are both wasted. So this presentation is also about kind of, how can we design a high performing hot water system, looking at distribution. And we also, when we talk about hot water distribution, a lot of times we think about the building type, so we kind of segmented it into, we have a residential hot water distribution, or we have a commercial hot water distribution. So residential would be like single family homes, or if you have a multifamily building with a water heater in each apartment unit, then we would refer to that plumbing architecture as, a residential type hot water distribution. And then if you have like a multifamily building with a central hot water system that's, serving the whole building, typically we would refer to that as a commercial distribution, commercial hot water system. So this presentation is really going to be just focusing on the residential side. I mean, there's some other aspects of commercial that we can get into, but I think that's a topic for another day. But on that thought, what distinguishes a residential type hot water system with a commercial hot water system? Is it the type of building that it happens to reside in? I would say that's a lot of times it's a misnomer, because can a hot water system in a commercial building resemble like a residential type system, and vice versa? And the answer is yes. So we could see like a small office building, maybe the office that you're in right now, maybe has a small 40-gallon water heater that serves a couple laboratories and a break room. The plumbing runs are not too long. Yeah, technically it's in a commercial building, but we really wouldn't call that a commercial hot water system. So now the $1 million age-old question, right? Why are we waiting for hot water? And this is a problem that I think exists in many homes in the US, and a problem that most people can relate to, right? You wake up in the morning, you turn on your shower, you go to wash your hands, and it seems to take forever for hot water to come out, right? And the reason that we're waiting for hot water is, over the past 40 or 50 years, the median US home has gone from about 1,600 square feet to about 2,500 square feet. So the average distance of pipe from where the water heater is to the farthest fixture in the house has more than doubled. I know in Texas, you guys, generally put the water heater up in the attic. In California, we have them. Where I grew up in Minnesota, we have them in the basement. Wherever that water heater is, typically now the trend is that it's getting farther and farther away from where it's being used. The number of fixtures have doubled. Pipe diameter has increased by 2 to 3 times. And then here's an important one. The fixture flow rate is continuously being reduced. I can just speak from experience that I remember when I first moved to California, and shower heads were 2.5 gallons per minute flow. And now in new construction, I think the requirement is 1.75 GPM, and it's even going lower than that, 1.5 the shower head. In some cases, 0.5 at the bathroom faucet. So this fixture flow rate in combination, the fixture flow rate reduction in combination with all of these other factors results in taking almost 20 times as long to get hot water in today's newly built homes than homes that were built, just several decades ago. And also we're wasting thousands of gallons of water per year just waiting for the hot water to arrive. What kind of hot water distribution systems are there? So let's take a look at some of the different categories of hot water distribution systems that we have to choose from. The one that is most standard is what we call standard trunk and branch. And just kind of as an FYI, when we talk about hot water plumbing or hot water piping, distribution piping, we'll refer to the piping almost like a tree where we have trunk lines, branches, and twigs. The trunk line being the major artery of hot water pipe that delivers the hot water. The branch line is literally branching off the trunk line and going to the fixtures. And then once it gets to the fixture, we call it the twigs that are actually going into the fixture. So branches, trunks, branches, and twigs is kind of the nomenclature that we like to refer to. Now, so the standard trunk and branch is where you have the water heater on one side of the house and it just dead legs to the other end of the house. And it's the most basic plumbing layout. It's easiest to implement. So in most homes, this is typically what we see. The problems with the standard trunk and branch is that it does have some of the longest hot water wait time and some of the longest waste, or some of the most wasted water. It's because typically that trunk line is a larger diameter pipe. And so there's more heat losses too. So we're wasting water and energy in these types of configurations. Another type of distribution system is what we call a compact plumbing system or a core plumbing system. And what's nice about these, and this is sort of the gold standard if you can achieve it, is to have the water heater more centrally located where the fixtures are not any more than about 20 or 30 feet maximum from that heating source. If you can do that, then you won't be wasting a lot of water waiting for the water to arrive, and you won't be wasting a lot of energy because there's not a lot of standing water in the piping. Now, this is a type of system that I grew up in my house in Minnesota, because the water heater was in the basement right in the middle of the house, and it just like literally went 10 feet to the bathroom and then 15 feet to the kitchen. So the pros is they're short runs, you get fast hot water, less water waste, and you don't need any type of recirculation system. Now, the cons of this one is that it's in many cases less practical to implement. For example, trying to place the water heater in the middle of the house. Typically, it's easier for a builder to put the water heater on one side of the house and then just run the plumbing in series. And it's definitely more difficult to achieve on a larger floor plan. Maybe if you have a smaller floor plan, it might be more achievable. So we're seeing, a lot of builders struggling to implement a compact plumbing design. Another type is a home run manifold. Maybe you've seen these before. This is where the pipe comes out of the water heater and then it goes into this large manifold. It almost looks like a circuit breaker box. And then you have a dedicated branch that's going to each individual fixture. What's kind of nice about this is that like you can isolate each fixture, right? So if you're doing repair work or whatever, you don't have to shut off hot water for the whole house. You can just shut off each fixture individually and work on it. It also has like it basically balances out all the pressure. The problem with the home run manifold though is that it uses about 2.5 times as much pipe as other distribution methods, so it's more expensive. It is has a lot more standing water in the pipes, and you still have the long hot water wait time, so it really doesn't resolve that dilemma. Last but not least, we have the recirculation system. And a properly designed recirculation system provides fast hot water and has the potential to save the most water and energy than any other distribution method. The cons to this is that, you know, if you number one, well, you need a recirculation pump, so you need to have something mechanical that's actually working it. And if that pump isn't controlled, it could come at a tremendous energy cost, and we'll go into that in more detail. So let's dive into hot water recirculation. So hot water recirculation is there because it decreases the time for hot water to the tap. It provides a lot of convenience, right? You're not sitting there waiting forever for hot water or doing something else. And it saves water. But alas, not all hot water recirculation pumps are created the same. So it turns out that there's quite a tremendous cost to operate a recirculation system. And I like to use the analogy of an iceberg, where the tip of the iceberg is the upfront cost of the pump. And then the operational costs are sort of like the hidden costs, the costs that you don't see unless you're really looking at your energy bills. So number one is the electricity to operate the pump. You know, if you have a pump that's, you know, let's say it's a 100 watt pump and it's running 24/7, you know, that can be a pretty good energy hog. But then you also have the heat losses through the distribution. So the more often that you're pumping hot water into your pipes and no one's actually using hot water, the more often your water heater is cycling on to make up for distribution heat losses. You also have some non-energy related issues as well. So the more often that you're circulating, the more often that you're going to be, you know, creating wear and tear on your pipes that could eventually lead to pinhole leaks, a worn out heat exchanger in your tankless water heater, pumps failing due to cavitation or airlock. So these are just some of the issues that can occur with excessive circulation flow. So now the question is of these, which is the highest cost to operate the recirculation pump? And if I had one of those little quiz things, I'd send it out, but unfortunately I don't. So I'm just going to tell you that 90% of the operation cost is from the heat loss in the pipes. So it is by far what is costing you the most is heat loss in the pipes, making your water heater cycle on more frequently. So that's what's causing the bulk of the energy loss. So the strategy then is, let's control the recirculation pump and turn it off when it doesn't need to run, and you will mitigate these heat losses. So there's different types of recirculation controls that have been available for, you know, for as long as pumps have been around. Well, first is no control at all, just continuous recirculation, and that's about the worst thing that you can do from an energy and from a non-energy, from a maintenance standpoint. There's time clocks, which put on a schedule for your pump, try to predict when you use hot water. But you know, timers are an interesting thing, right? Like hot water use in your dwelling unit can be completely unpredictable and spontaneous, right? I mean, we sort of know when we're going to take our hot water shower in the morning, but outside of that, can you predict when you're going to use hot water? And most people, the answer is no. It's a spontaneous type of event. We have temperature regulators, or aquastats as they're known as, that turn the pump off. The reg basically turns the pump on and off based off of a temperature deadband. You have a combination of the two. You have variable speed drive pumps. This is something that's kind of newer to the industry. Variable speed drives. Now you also might hear the term ECM motor pumps, which is known as it's an electronically computated motor. An ECM is actually not a pump control. It is a type of pump motor. So if you hear ECM, it still means that the pump is just running, continuously. It's just that the type of motor that it's using uses about half the electricity. So it is the preferred motor to use with a recirculation pump, but it's not actually controlling the pump. Now, a variable speed drive we often associate with ECM motor pumps, and that's just basically turning the speed of the pump, higher or lower based on, times of demand. And although this has an impact on the electricity consumption, it still means that the pump is running constantly. It's still pumping hot water out. There's these other products that we've seen on the market that are so-called smarter learning, which, supposedly they learn your habits or behaviors and turn the pump on. But as I stated before, hot water use can be completely unpredictable. You could go on vacation and, I don't think that the pump is really going to know that. I don't know, maybe sometime in the near future with the advancement of AI, it can become, that smart and intelligent. But until then, we just haven't seen anything that can accurately predict when hot water is being used. And then finally, there's demand controlled. And only the demand controlled systems accurately matches the operation of the pump to when hot water is actually being used. When do you not need to operate the recirculation pump? So if you don't need hot water, right? If you're at work, if you're on vacation, or even if you're at home and you're just like watching TV or, doing something else, that pump does not need to be running. And also if there's already hot water in the line, so if somebody just used hot water, or if, once hot water is flowing out of your faucet, then the draw flow will already move the water through your pipes. The pump no longer needs to run. So you only need to turn the pump on right before you need it. So the only time that pump needs to run is during that transitional period where, hey, I want hot water and the hot water in my pipes have cooled down to an unusable temperature. That's the only time the pump needs to run. And then it only needs to run for about 30 to 60 seconds before hot water gets there and it can shut itself off. So a demand controlled system uses a sensor to turn the pump on, indicating demand for hot water. And this can come in different varieties. It could be a manual push button switch. It can be a motion sensor. It can be a flow sensor. It could be a remote wireless activator. It could be a voice activator. It could be like, you telling your Siri, hey, Siri, get me hot water. It could be anything like that. Oops, I just turned on Siri. I shouldn't have said that. It also uses a temperature sensor to turn the pump off once hot water has been delivered. So one sensor turns the pump on and another sensor turns the pump off. It will work with any tank, tankless, or heat pump water heater. So here's a schematic of a demand controlled recirculation loop configuration. And you can see where you have activation sensors at each fixture in the house. And they either are wired back to the pump or it could be wirelessly. You can see there's a temperature sensor on the return line, and that return pipe is going to be connected into the cold water. Typically, it's connected into the cold water makeup pipe for the water heater. Another way you can do it is if you don't have a dedicated return line, and you want to install a on-demand system in a regular trunk and branch type of plumbing configuration, you can do that by installing, well, we refer to it as an undersink kit. There's other products out there that have something similar, where you cross-connect your hot water pipe into your cold water pipe. So basically, you have this cross connection from your hot into your cold, and there's a little temperature sensor that is going to tell, that's right here at the point of use, that says whether or not this hot water line is hot or not. So if I walk into my bathroom, I push this button and it says, no one's used hot water for a period of time. Usually it takes about 15 minutes for the hot water line to cool down to ambient temperature. Then that pump's going to turn on, and it's going to simultaneously pull hot water from the water heater and take it through your trunk line. And it's going to take that cold water that normally goes down the drain and pump it right back into your cold water pipe and send it right back to your water heater. So what this little kit does is it creates a circulation system using your existing hot and cold pipes. Now, with an on-demand system, it's only looking for about a 6 to 10 degree rise in temperature. So if let's say your hot water line was 60 degrees, right? First thing in the morning, 60 degrees, and the pump turns on, it's only going to run until it hits about 66 or 67 degrees, because just that short rise in temperature indicates that the hot water is just seconds behind it. So the pump is actually going to turn off before you start pumping any in your cold water line. So, after about, 30 to 60 seconds, pump shuts off. You have hot water throughout your entire trunk line, but you still have cold water in your cold water line. So this is what a under sink sort of configuration looks like, and it's excellent for any retrofit of an existing house or a commercial building. We've actually installed these in a lot of commercial buildings that had a problematic branch line. The design, the design of the plumbing was just done, so that it was impossible to get hot water quickly. And so you can actually install this at the end of any fixture or at the end of any trunk line, whether it's residential or commercial. The problem in most cases is that you need to have a little power outlet here. So you need to have power underneath that sink or nearby in order to operate the pump. So what are the benefits of demand controlled recirculation? Well, compared to other types of recirculation pumps, this pump will only run about 10 to 15 minutes per day in total. So when you compare that to circulation systems that run, let's say, continuously, that's well over 90% reduction. That's like 98% reduction in heat losses and pump runtime. You're going to get a much longer useful life of the pump and a lot less wear and tear on your plumbing system. You're going to save somewhere between 3 to 10,000 gallons of water per year. This is an estimate by the U.S. Department of Energy. It will meet your IECC energy code requirements, and we'll talk about that momentarily. And the energy to actually run the pump is less than $5 a year. So, going back to that iceberg analogy, with most recirculation systems, you're gonna save about the same amount of water. The difference is the energy it costs to circulate that system. And in most cases, the energy is so much higher that you're net negative, right? You might be saving some water, but it's coming at such a huge energy cost. And as we discussed about the water and energy relationship, is that you're going to be at a net negative. You're actually, you're never going to have a payback. Whereas with an on-demand system, the water savings and the energy savings you're actually going to get a payback on that system. And you're going to get a much longer useful life, as I said, less wear and tear. Any questions so far?
No, there's nothing that's come in yet.
Okay.
But I liked where that went a second ago with the comparison of, and I don't normally have people think that way, is that the energy it costs to reheat the water that was wasted, those pumps do a fraction of that, which that's a great point.
Yep. And I'm going to show you some really compelling numbers here in a future slide. So but right now, let me just talk about some of these energy codes and building certifications. A lot of builders now are trying to achieve a kind of go beyond the energy code and go to a high performing home certification like LEED, or WaterSense now has a new guidelines for energy, water efficient homes. And then the DOE has the Zero Energy Ready Homes program. So all of these require demand recirculation. If they're doing recirculation, you have to be demand controlled. So So this is the language that you'll find in those guidelines, is that the circulating pump may not operate continuously on a timer or on a temperature aquastat. So it's pretty clear that those types of controls are prohibited. Circulating pump must be demand activated by a momentary contact switch, moments for flow switch door command. And after the pump starts the pump up to operator temperature until it's either a no more than a 10-degree rise in temperature, 5-degree lockout. So it's become, more like more where before there was a lot of ambiguity. So here's the chapter for lead to get lead, get 2 credits for efficient hot water distribution. So if, let's say you have with the like, let's say you have 3/4-inch pipe, 3/4-inch hot water pipe, you cannot have more than 8 feet of a well, let's see, you cannot have the farthest fixture be more than 21 feet away from the water heater. Or if it's a oh wait, no, this is for multifamily. I'm sorry, single family is yeah, this is for single family. It can't be more than 8 feet away from either the source or the circulation loop. So it's really difficult to achieve some of these requirements in terms of standing water in the plumbing. So it really is advantageous to have a recirculation loop where you can run because they consider the main circulation loop as the heating source. Whereas if you can keep the branch lines within about 16 feet of half-inch pipe, then you're not going to waste more than a couple of cups of water. Water Sense says that you should have no more than half a gallon of water may be stored in any piping or manifold between the hot water source or any hot water fixture. Recirculation systems must be demand initiated. They may not be solely timer or temperature based. California, we have an energy code called Title 24, and this was the first state that required demand recirculation controls. And it says, that if you're building, it doesn't say that you have to put in a recirculation pump, but it says to the builder, if you are putting in a recirculation pump, then only demand controls are allowed. And before, when this first came out, there was still a lot of confusion. They thought, well, a timer is basically a demand control because it tells us when there's going to be demand in the morning. And then, finally, the Energy Commission had to be more specific about what a demand control was. So they said, okay, a demand control is on demand, meaning that the pump operation shall be initiated shortly prior to the hot water draw, that the manual controls shall be located in the kitchen, bathrooms, and any hot water fixture that's at least 20 feet from the water heater. And then after the pump's been activated, the controls shall allow the pump to operate until the water temperature has not seen more than a 10-degree rise of temperature or a 105 or 102-degree lockout. And then also they have a provision in there that says that if the pump runs for 5 minutes, it will automatically turn off by default. And the reason that they have that in there is because one of the most common reasons for pumps to fail is if there's airlock, right? So if there's air in the return line, the pump will be running, but it won't actually be moving water. When that happens, these pumps will burn out. So this 5-minute lockout is to ensure that the pump doesn't burn out. So now what about IECC? This is the code that that Texas, the state of Texas conforms to. I believe Texas has adopted 2021. And I think it is kind of up to each jurisdiction to decide. But so
Gabe, sorry, Gabe.
yeah,
Yes, the state is still on 15. We hope that's going to change the next legislative session. But yeah, we're home rule state.
okay,
So all cities and jurisdictions adopt and amend how they see fit for their community.
okay. Well, the good news is that this language that we see here started in 2015. So this is the language that if you look up IECC, the most recent language that you conform to, you're going to see that controls for circulating hot water system pump shall start the pump based on the identification of a demand for hot water within the occupancy, and that the control shall automatically turn off the pump when the water in the circulation loop is at the desired temperature and when there's no demand for hot water. And then right below this, it actually gets even a little more granular, more definition, where demand recirculation systems is a control that start the pump upon receiving a signal from the action of a user of a fixture or appliance, sensing the presence of a user of a fixture, or sensing the flow of hot or tempered water. So basically saying, okay, it's either going to be a manual push button, or it can be a motion sensor or a flow sensor or something similar. And we've seen this happen over the years with IECCs, that they've been becoming more and more explicit. So if you go back, every 3 years, IECC changes their energy codes. And what was interesting about this specific, part of the energy code, which, frankly, most often gets overlooked. It's actually gone through the most change of almost any code revision over the past, decade. So every 3 years, we've seen it becoming more and more defined, where, today we actually see it saying, okay, it has to sense demand, by sensing the presence of a user, or the act, or sense demand within the occupancy. And that wasn't the case before. And it was the same thing like what we saw in California. Was there was so much ambiguity that it just became status quo. Nothing really changed. So there's 4 main components to a demand controlled pump. There's the pump, there's the demand controller, and this can either be a separate, control box, or it can be integrated into the pump depending on the manufacturer. There's an activator, and these can be wired or wireless, and then there's a temperature sensor. And it also should be noted too is that an on-demand pump should be sized for the application. It's not necessarily one size pump fits all. You want to make sure that depending on the size of the house or the size of the recirculation loop, that you have a pump that's going to, circulate the hot water from a cold start, in a reasonably fast manner, right? So we have some guidelines as far as what pump to use, and other manufacturers have their guidelines too. And so this is just kind of like a rough rule of thumb. So just something to keep in mind. Now, what are some of the methods for demand controlled pumps? There's, as I said, there's hardwired manual activators. So this could be like a little doorbell button, or a rocker switch, or a push button activator. And you press it anytime you want to activate the system. It's a momentary contact switch. So it's not like a light switch where, it's just you flip it on and off. It's momentary contact, more like a doorbell. And if there's hot water already in the line, even if you push that button, the pump is going to remain off. So the temperature sensor will always override the demand switch. So the activation switch may be located near any hot water fixture that is at least 20 lineal distance feet from the water heater. So a lot of builders like to put one next to the fixture, or they'll put it next to the light switch when you walk into the room. There's other types of switches that give you an indication when there's hot water in the line. So this is something that's unique to our AutoHot product, is that if you walk in the bathroom or kitchen and you see that this light is on, it means that you have hot water in your line, and all you have to do is just open the fixture, and hot water should come out in a few seconds. And then after, 10 minutes, 15 minutes, whatever the case, when the lines start to cool down, then this light will turn off. And that tells the occupant, okay, I need to prime my loop in order to get hot water. So you just hit the switch, it'll start to blink, indicating that, circulation's happening. And then once it's ready, it'll be solidly lit. So manual activators ensure that water circulates only when there's hot water demand. But there's also motion sensing activation. So if you wanted to have a fully automated system, this could be a good option for you. It doesn't require any manual activation. It only turns the pump off if there's motion sensed and the return line temperature is not hot. So again, let's say you have one in each bathroom, right? You walk in your bathroom, it turns on, the pump and tankless water heater now are delivering hot water throughout the house. But if somebody walks in into another bathroom, like 5 minutes later, the pump isn't going to turn on again, because again, once the temperature says the loop is satisfied, you could keep walking in front of that motion sensor and the pump will remain off. So here's a picture of what that motion sensor could look like. And there's other types that are like recessed in the wall. We've seen them placed under like kick plates, underneath like cabinets and things like that. So you can put them in areas where they're not really obvious. And you can also adjust them too, so they don't like track pets or small like children. So you can adjust the range so that it only picks up like adults. Now here's a wiring diagram of how you would want to do the wiring. You want to make sure that it's wired in parallel and not in series. And you want to make sure that the wiring is run all the way back to the controller, so that this way you can test the continuity of each sensor individually. In some cases, we've seen where they've connected all the wires into one main branch, one branch circuit all the way back. And then if there's like a short somewhere, then it's impossible to figure out where it's occurring. So this is the best way to do it, is to have to run a single line from each sensor all the way back to the controller. There's also wireless activation. So depending on the manufacturer, the wireless range can be, it can either be Bluetooth, which is, typically a shorter range, like usually 80 to 100 feet. We like to use RF, which has a range of about 1,000 feet in open air. So generally speaking, these will transmit very easily through interior walls of wood frame construction in really, any size house. And you can use these in conjunction with wired switches too. So recirculation systems on a tankless water heater work very well. In fact, you kind of get the best of both worlds. You have on-demand pumps with on-demand water heating. And it's funny too, because, to this day, when we still meet people that think, well, I'm going to change out my tank water heater with a tankless so I can get my hot water faster. Because they hear on-demand water heating, and they think that it's going to be, instantaneous hot water, which is, definitely not the case. And in fact, if you change out your tank with a tankless, oftentimes you'll actually have a little bit longer wait time for hot water, because it takes a few seconds for the heat exchanger to heat up. These are kind of like the perfect combination of efficient water heating and efficient circulation. A lot of tankless water heaters now do have a built-in recirculation pump. Many of them do not have the demand control, though. It's run based more on a timer-based system. So if you are using a tankless with a built-in pump and you want to meet IECC, just make sure that it has an activation switch, that it's an on-demand system. But personally, I think that it's better to use an external pump. Number one, you can size the pump. So with a tankless, usually they have just one very small pump that's internal, and they're using it for every house that's from 2,000 square feet to 5,000 square feet. And you definitely want, when you get to bigger floor plans, you definitely want to get a bigger pump. So I think it's better to have an external pump that you can size, and also just from servicing and replacement standpoint, it makes it easier. So if you're an inspector and you want to verify if a recirculation pump is demand control, what do you look for? Number one, first and foremost, is, are there any activation switches or sensors? So you just want to find out from the builder or from the homeowner, like, okay, where are your activation switches? In California, they are requiring, at a minimum, you have to have one at the master bathroom in the kitchen, because that's where like 80% of all hot water is being used, is at the kitchen and master bath. So they have to have those two switches, but they're also saying then, they're starting to say now that if it's at least 20 feet of lineal pipe from the water heater, it needs to have a sensor as well. So just make sure that there's an activation switch, and then also make sure that there's a temperature sensor on the return line. Sometimes it could be built into the pump. Sometimes you'll see it strapped onto the return line like an aquastat. And then if that return line is hot, then the pump should definitely not be running, because with any on-demand system, once the return line is hot, then the pump stays off no matter what. And then just keep an eye out if the pump is a known manufacturer of demand systems. We have our auto hot system, but there's also like the Takeo Genie is an on-demand system. ACT demand, which is, used to be called Metland. I'm sure most people have heard of the Metland system. Grundfos has a little on-demand system as well. So just be on the lookout for those systems. Okay, so other than like the residential, we see a lot of commercial applications that can utilize a demand recirculation pump, but it's not a commercial hot water system. So we see a lot of gyms, we see a lot of office buildings, schools, admin buildings, where we see smaller water heaters, shorter plumbing runs. Maybe serving, maybe if it's a gym and you have a couple of locker rooms, all you need to do is stick, a motion sensor at the entry of each locker room. And that makes sure that, that ensures that as soon as somebody walks in, there's occupancy, it's going to make sure that there's hot water in that line. And then, it's actually better than a timer, right? Because as soon as that last person leaves, the pump shuts off and it's not going to turn on again until that first person, the next day walks in. So here's a case study, a real example where we retrofitted a hotel that had a pump that was only serving the commercial laundry room. So this was not the pump that was serving the rooms, the hotel rooms, but rather it was a circulation loop that was just for the commercial laundry room. And we observed that it was just running continuously 24/7. And it was completely unnecessary. So what we did is we installed the controller, and this is, you can get the controller as a standalone unit that you can use on an existing building's existing pump. So the pump was already there, and all we did was we added the controls. We tied a little temperature sensor on the return line here, plugged the pump into the controller, and then we put this little wireless motion sensor inside the room. So it only circulated the hot water when people were actually doing the laundry there. So at night when nobody was there, it stayed off. The return line was allowed to cool down. The pipes were allowed to cool down, and none of that water was being circulated back into the tank and, causing the boiler to, continuously fire up. So now instead of running 24/7, that pump is only running about maybe 10 minutes per day total, and achieving significant energy savings. And we can also retrofit buildings that have, like I said, have existing what we call legacy plumbing issues, where maybe the design of the plumbing wasn't great, and we actually run into a lot of commercial kitchens that are subject to health inspections, health inspectors, where they have to get 120-degree water out of any of their, prep sinks within a certain period of time, like usually under a minute. And we've actually seen many instances where they're just not able to do that, and they're not able to pass their health inspection. So in that case, you can do the little under sink retrofit and use a little motion sensor. So when people are in the kitchen, it primes that branch line with hot water and ensures that the hot water is always there. Excuse me. Okay, so now I want to talk about optimized recirculation loop configuration. So what do I mean by that? So just because you have a recirculation loop does not necessarily mean that it's going to be ultra efficient. And what you'll read in a lot of like the LEED and in Energy Water Sense, all of their guidelines for designing the recirculation loop, they say things like, number one, avoid 90-degree elbows wherever you can. Instead of a 90-degree elbow in your pipe, have a sweeping radius elbow, because then you have less friction loss. you have better circulation flow, and you have less energy losses that way. So you want to avoid hard 90s. You want to minimize the recirculation loop trunk line to about 3/4 inch. And then you want to keep the branch lines to only 1/2 inch. Now, if you do that, and if you can minimize the distance of the branch to within about 15 or 16 feet from the circ loop, so the distance from the main trunk line to the fixture, if you can keep that within about 16 feet, and then once you prime the loop, then you'll never waste more than about 2 cups of water at any fixture in the house or in the building. So that's the goal, is to design the recirc system in such a way that you can save the most amount of water as possible. And it goes without saying that all the intended loop should be insulated to a minimum R4 value. On the return line, there are certain things that you have to have in order for it to work properly. So, you've got your pump here, you've got your temperature sensor on the return line. You should have ball valves or isolation valves so that, when you need to replace or service the pump, you can easily just, take it out without shutting off hot water to the whole building. You need to have what's called a bleed air out of the return line. So this is a common issue with recirc systems, is getting air where, it can't work its way out. Like if you have air in the supply portion of the loop, it will naturally find its way out through a fixture, and you'll see like a shower or a faucet will start to cough out that air. But because you have check valves on the return line, you don't have any backflow. So once that air comes into the return line, then it's basically the pump is not able to move water, and it's not able to go backwards through a fixture. So it just gets kind of trapped there. And then what happens is that this pump will burn out. So if you experience that your system is not, you're waiting a long time for hot water, and if you go into your mechanical room or you go to wherever your pump is, and if you touch it, and if it's really hot to the touch, but your return pipe is like cool or just ambient, that tells you that this is overheating, and you have to bleed the air out of the line. So it's a very simple fix. It takes all of 2 minutes. So here's what a return line would look like in a house. You've got your temperature sensor back here. You've got a shutoff valve on one side of the pump. You have another shutoff valve here. Here's your bleeder line right there to purge out the air out of the line. So this just gives you an idea of what it would look like, a return line configuration.
Gabe,
Yes.
on that bleeder line, is that something that should be a scheduled maintenance, or is that something that's just in case you have the issue?
That is a good question. I think, okay, if you have tankless water heaters, you should definitely flush out that heat exchanger once a year at a minimum. And depending on the water quality. Now, if you have a good water treatment system, you might not need to do it every year, but you want to do it after the first year, just to see how much scaling there is. So that's definitely part of your maintenance, is to flush out the heat exchanger of the tankless. It would be a good idea to do that, but if you determine that your system's working well, you push the button, the pump turns on, you can feel the pipe getting warm and then the pump shutting off, then you know that there's no air that's obstructing the circulation flow. It's not an issue. The only time that you really need to purge the air out is when you're not getting hot water. You're calling for hot water, and it's still taking you 2, 3, 4 minutes to get hot water. Then it's like, something's not right. So when you're going through kind of like the troubleshooting is, number one, do I have continuity with my activation switch? Is my controller or is my pump getting the signal for demand? That's the first step. And then the second step is, okay, it is. The second step is, I'm going to plug the pump directly into the outlet. Is my pump actually working? And if I can see that my pump is actually running, then I'll be like, okay. But like the telltale signs, again, is if the return line is cold, but the pump is really hot, because it means that it's been running but not moving water. And these wet rotor pumps, need to have fluid go through them to kind of, cool them down. And so that motor will just overheat. So if the pump is really hot to the touch, and sometimes it'll make like a noise too, like kind of like a rattling noise. That's another indication of air in the line. Those are signs to tell me that I need to open this up and I need to purge the air out of the line. Now, what's really important when you do this exercise is that you have to have this shutoff valve closed. Let's say this shutoff valve was open and there was no check valve right here. Then if I open this up, the only water that's going to be coming out is going to be this cold water. It's just going to be short circuiting, right? So what I want when I open this bleeder valve, what I want is I want to induce all of the water in the return line to come out of this bleeder valve. But if I can't isolate, or if I can't shut this off, then it's just going to be cold water coming right through here, and then you're never going to effectively bleed the air out. So I've actually seen a lot of plumbers struggle with this. Like, hey, I bled the line for 10 minutes and it's still not working. Well, if you didn't shut this valve off, there's no checker, then yeah, that's going to be, you're not actually bleeding air out of the line. So that's an important step.
Makes sense. Thank you.
So what's a water energy? Yeah, you're welcome. Good question though. So here is a table showing the differences in energy loss of a demand system versus other runtime operations of other types of pumps. And this is assuming a 100-foot long loop, 50 supply, 50 return, that the circulation rate is only 1 GPM, but most likely these flow rates are going to be much higher than this, which means that the energy losses are much greater. It's assuming a temperature drop of 5 degrees from supply to return, assuming 50-watt recirc pump. Now, if you look at a demand controlled pump, it's only running about 10 to 15 minutes tops. And sometimes it's a lot less than that, to how many times you have hot water activity in the house. And you can see that it uses about 3 therms of gas. If you have a continuously running pump, you can see that it uses about 300 times the amount of energy to move the hot water, in terms of heat losses. So it is a substantial amount of energy loss when you're running the pump. I mean, even like 4 hours a day is more than 30 times the energy loss. And then, of course, it's the electricity to run the pump. So this is the electricity to run the pump, and then these are the distribution heat losses. So this table just kind of like illustrates just how, the more often you're running that pump, how much more your water heater has to consume, gas to, maintain the system, the system. Oak Ridge National Lab did a study of on-demand systems, and they modeled it where if they assumed 150,000 houses had an on-demand system, that they would see a total savings of 550,000 million BTUs of savings per year, and 1 billion gallons of water saved just by retrofitting that number of homes. The average, they said on average, a home could save about 7,000 gallons of water per year. And this was a more of a conventional. This was a little over 5,000 gallons of water per year. And in some cases, it's going to be higher. In some cases, it's going to be lower. So, we're seeing the average is around 6,000 gallons of water per year. Lastly, I wanted to just talk real quickly about heat pump water heaters. I don't know if this is becoming a big thing yet in Texas. I can tell you in California, it's been a seismic change in the plumbing industry where, when I first got into this, we were just making the transition from tank to tankless water heaters. It became a prescriptive requirement per the energy code about, I don't know, maybe 10, 12 years ago. And so it was quite an adjustment to go from tank to tankless water heaters. And now we're seeing the pendulum completely swing in the other direction, back to tank water heaters. But in this case, we're going to electric heat pump water heaters. And it's what's really interesting, just real quick, is that it's completely different than a gas water heater. A heat pump water heater, if you're unfamiliar, it transfers heat from the surrounding air to the water using a refrigeration process. It's 2 to 4 times more efficient than even the most efficient condensing gas water heaters. So if you have let's say you have a condensing tankless water heater, let's say you have a Rinnai water heater that's 97% thermal efficient, you can get a heat pump water heater that has an efficiency of about 300% thermal efficiency. So what that means is that for every 1 unit of energy that comes in, you're getting 3 units of hot water going out. And so they're super, super efficient when they're running properly. There's no combustion in the water heater room. There's no carbon emissions, so you never have to worry about carbon monoxide poisoning. You never have to worry about venting out that toxic air. The one thing you do have to consider though is that if you look up above, there's like a little blower fan, and this is blowing out cold air. So you want to make sure that you have enough space in the room to allow that cold air to kind of dissipate. If you have your heat pump trapped in a small little broom closet and you don't have like louvered doors, then what it's going to do is it's just going to keep pulling in the cold air, and it's going to make the system less efficient.
Babe,
Yeah.
so Texas is still big on putting water heaters in the garage. And when people start to realize that these things will air condition your garage,
Oh,
so
they're
you
going to love
can
it.
work on the car much easier. Yeah,
They're going to love it.
it's gonna be awesome. I mean, we're still an oil and gas state. It's cheaper to put a gas water heater in. They're cheaper to replace at Home Depot.
Yep.
But yeah, once these things become, hey, you can air condition your garage for not adding an air conditioner, and it works great. So yeah,
Yeah.
these are neat.
I'm telling you, and I think there's something they haven't really come up with it yet, but they have to figure out a way to use that cold air to put it back into the conditioned space. We got involved in some projects with some hotel boiler rooms where we replaced the gas boilers with a bank of heat pump water heaters. And now when you walk in that boiler room, it's like a meat locker. It's like a walk-in refrigerator. It's so cold. And the problem is trying to vent that cold air out. So yeah, I mean, I think, but when it's in a garage, you have plenty of, I think each water heater company says that they want to have like 400 cubic feet of space, which is, a garage is going to have more than enough space. And like you said, it's going to like make that garage like a completely conditioned space in the summertime. So it's going to be great. Yeah.
Yep. One quick thing, though, we have a question that came in back a few slides ago,
Yep.
talking about that bleeder valve that was there.
Yep.
Benjamin asks, should the bleeder line have been at the highest point? Or does it need to be at a highest point in the loop?
No, so I think what you're thinking about is there's a type of bleeder valve that kind of self purges it. It's called I'll tell you what it's called. I know what he's referring to though. And in that case, yes, you want to have it at the highest point. What it does is it tracks when there's air in the line, and it actually purges the air out automatically. So you can put those in, but then you do have to have it at the highest point. And in some cases, like if you're running plumbing through like the attic or whatever, then it's not going to be super practical to have that self-purging bleeder valve in. So that's why I think they should always have, if they can't do that, then this is going to be the next best thing, is to have a manual airline, because then you can put those anywhere. The only caveat, it has to be downstream of the pump. It can't be before the pump. It has to be downstream of the pump. And then it has to have some type of either a check valve in front of it or a shutoff valve, so that when you open it, you're not getting any flow from the other side. But yeah, that's a great point. There are types of bleeder valves that will self-purge, that will do it automatically, but they need to be at the highest point of the loop. And in some cases you can do it and it's practical. In some cases it's kind of hard to do. I hope I answered your question.
I think you did. Thank you.
Perfect. So the other thing I want to talk about with these heat pump water heaters is that a lot of them are what they refer to as hybrid systems, where it has a heat pump, but it also has these heating elements where if the heat pump's not able to keep up, it will switch over to electric resistance mode. And when that happens, all of your efficiency is just kind of go off a cliff. And basically hot water recirculation will diminish the heating capacity of a heat pump water heater. So with a demand system, it's the only one that will work with a heat pump water heater because it's going to limit the volume and the temperature of the return water going back into the tank. So it won't adversely affect the recovery, the heating recovery, and it won't adversely affect the COP or the coefficient of performance, which is basically the efficiency level. So most of the major manufacturers of heat pump water heaters like A.O. Smith and Rheem and Bradford, they're all saying, if you're going to do a recirc pump, you should really do an on-demand recirc pump if you want to keep it in the heat pump mode. So here's some guidelines by A.O. Smith for installing their heat pump water heaters, and they basically just took the code from the energy code and they drafted it into their operation manual. So a recirculation system not following these guidelines could lead to longer continuous heat pump runtimes and a reduction in available hot water. So if and when heat pumps become a big thing in Texas and they're using recirc pumps, it's even more important to have an advanced demand control on that to preserve the functionality of that heat pump. So anyway, that's my presentation. I hope you guys learned something new today. I'm happy to take any questions. And yeah, thanks very much for your attention.
We appreciate it, Gabe. Thank you. I mean, I don't know a lot about water heaters, but I learned a lot about water heaters today and kind of how they work, and especially demand recirculation pumps. One question about the motion sensors or occupant sensors. Could those be, and I'm only thinking about this because the other code requirement for light controls, can
Yes.
they be combo systems where those motion
that's
occupant sensors can be tied together?
That's a great question. We get that a lot. The answer is probably not, because it's using a different type of switch where it has to be a normally open momentary contact switch. So with a light, it's with a light, I believe it is normally closed. Or no. Well, yeah, I don't think it's going to work. We've tried to integrate light switches before. We haven't found one that works. It's an interesting idea, though. It's an interesting thought about like, hey, how can we have one sensor be able to kind of control multiple things? Maybe there's a way to do it, but it would not be using a conventional light sensor. It would have to be something that would be like slightly modified.
Yeah, because I can see we've got another webinar coming up, I think next week, talking about more controls, but a lot of it is dealing with HVAC controls for occupants. But I can just see in the near future. So now you've got lighting controls, water temperature controls for occupant, and then you got HVAC controls. A lot of this kind of blending in together for one sensor. So
absolutely. And I think that's the direction that we're going, right? Everything's sort of talking together and working together as a, one, integrated system, IoT, but yeah, it's got me thinking that, we should start to, look at other type of motion sensors to see what can work with, both the hot water pump as well as lighting and other, feature HVAC. But yeah, that's a good point.
And I take it there's not yet, maybe there is in the future, maybe they're talking about it, but basically just a monitoring system where you could actively see which pumps are running or how long they've ran.
Yeah, we actually have that feature. One thing I didn't go through in this presentation was our commercial system that we have for multifamily buildings and hotels and larger, like real commercial hot water systems. That's a different controller that we have that actually does remote monitoring with alert notifications. So it's actually a really cool platform. You can see some demos on our website that show all the different data points that we can track and monitor. And if the boiler shuts down, if the pump stops working, it will send alert notifications to let you know that, hey, something's not working right. So, we hope to eventually incorporate a lot of those elements into the residential version, so that a homeowner has a lot more information about like how often their hot water system's working and how much energy it's consuming and so on and so forth. But yeah, I think yeah, that's the other trend that we're seeing in building automation is everything being monitored and then optimized controls. And like everything, it always starts on like a very high level with like the biggest, where there's the most energy waste and the most expensive issues. And now we're starting to see those controls being implemented in smaller buildings and even down into like single family homes where before it might have not made economical sense to you know put controls in. Now it's like we're able to see it actually like pencil out.
Right. And one last question I have, and I know this is going to be just an occupant learning lesson, but
Mhm.
let's just say you get up in the morning, you walk into the kitchen, you're going to do your morning thing, the occupant sensor kicks on, the pump starts to run, and you normally just kind of slap the hot water side open because you usually just let it run. But
Yes.
so how long kind of just an average, if once that pump kicks on, I mean, you're not going to open the hot water side and it's now 120 degrees,
Right.
right?
Yes. Yeah. Yeah. That's a good point. So with any demand controlled recirculation loop, there's like a priming period, right? So it takes a certain amount of time to prime the loop, right? So the idea is that you activate the motion detector or you push the button and you let it run for a minute, right? You just let it run for a minute. We do have those like little indicator switches that will the light will turn on when hot water is ready to go. But let's say you didn't have the patience. Let's say you just walked straight into the bathroom and you turned on a fixture, right? Well, the way that the pumps operate is on a performance curve where when there's more head loss, the slower the pump circulates, right? The slower the water flow. But when you open up a faucet or when you open up a shower, then now you have water coming out of the fixed out of the you go from a closed loop to an open loop system, and now the speed of that flow is actually faster. So you actually get higher velocity when it's an open loop, when water's coming out of the system. So let's say, just hypothetically, let's say you hit the button, the pump turns on, and normally it takes a minute for the loop to get fully primed. Well, if you turned on the faucet right away, it might only take 30 seconds to get primed because now you've increased the velocity of flow in the pipes just by letting water out. I would say, the rough rule of thumb is that it will take somewhere between 30 to 60 seconds for a loop to get primed. And it really all depends on the size of the loop, the size of the pump, the size of the pipes. So it's not just the lineal feet, but it's also the pipe diameter. Is it 1 inch? Is it 3/4? Is it half inch? And then also like, the other little things like 90-degree elbows. They say that for every 90-degree elbow in your plumbing, it's the equivalent of adding 3 extra feet of pipe. So, the goal is to get hot water as fast as possible to minimize the wait time. And so that's what I wanted to kind of illustrate in this presentation, as it's not just about the pump. It's really and mostly about the design of the plumbing. So hopefully if if you all get a chance to look through the WaterSense guidelines for efficient hot water distribution, it actually lays out some of those features, of like how to lay out the plumbing versus just using a on-demand pump.
Right. And then I liked you talked about making sure it's insulated, but I know from a code standpoint, from a difference between a lead standpoint, is like for lead, you want it all the way to termination. So it's going to be insulated even in the interior wall. But in code, it's only going to be insulated to the top of the wall. Do
Yep.
you recommend it being insulated all the way to termination?
I mean, here's the thing. If you're doing new construction, you got one shot to do it right, because that
Right.
plumbing is going to be the way it is for the next 100 years. So, you absolutely should insulate all your hot water pipes, as mainly the trunk line. And well, yeah, the code here in California is that if it's anything 3/4 inch and above, it's a mandatory requirement that it has to be insulated all throughout. If it's 1/2 inch, then it does not. So if a 1/2 inch branch line does not need to be insulated. But the main trunk line, if it's a recirculation loop, or even if it's just like trunk and branch, standard trunk and branch, if it's 3/4 inch and higher, it has to be insulated. And why is insulation important? Is because it significantly reduces the cool down rate of the pipe. So if you have a pipe that's uninsulated, right, and you just primed it, and it's 100, and you just pulled 120-degree water through that pipe, it might take about 10 minutes to cool down back down to ambient temperature. Whereas if it's insulated, it might take 20 minutes for that pipe to cool down, right? So it's a minimal investment. It has a huge amount of payback in the long-term picture. Pipe insulation, minimum R4 is probably the best bang for your buck in terms of saving energy.
Yeah, and we in Texas learned the hard way about not properly insulating with the cold snaps that we have that froze the pipes. So last
Oh
question
yeah.
I have is, we don't see in new construction them using copper anymore. It's the PEX pipe. So does this
Yep.
change anything with requirements of what you have?
Not at all. No, we see PEX. PEX has basically been the norm here in California for at least the last decade, maybe even like 15 years or so. It's all PEX out here. And I suspect that's most of the country now is going to PEX. The thermal losses in PEX pipe is just as bad as copper pipe. It doesn't, you might think that because it's plastic versus metal that it doesn't transmit heat as easily, but it actually does.
Yeah.
So yeah,
Well, I
the
think
energy losses.
I think its advantage too is you're losing those 90s you talked about. More of it is a sweeping because they don't put a
Yeah,
90 in it unless they have to.
exactly. So
Yeah.
we see a lot smoother flow in PEX than we do copper with the hard 90s. And then just also like there's far less occurrences of pinhole leaks and things like that you're gonna get with PEX.
Right.
So PEX is definitely a worthy replacement for copper. There's some debate going on about whether PEX is better from a health standpoint. Copper has antibacterial, properties. I mean, there's a reason copper has been used in plumbing for 3,000 years, is because it's, for sanitary reasons, it's got antibacterial properties. And, there's some other fear that like with PEX or other types of plastic piping that especially in hot water systems, there could be some plastic leaching going on. I mean, there's nothing that really shows anything, one way or the other. But I think PEX is perfectly fine, but no matter if it's PEX or copper, you want to insulate it. That's for sure.
Very good. Well, thank you guys very much for this. This was very informative. I appreciate it.
Thank you. I appreciate the invite and appreciate everyone's time today and attention. And if you have any questions, here's my contact info. Please feel free to send me an email or give me a call.
Yeah, I changed the screen on you, but it was up there for a
Oh,
while. I guess, can you share this in a PDF form so we can give it out to with our
oh,
survey email?
absolutely. Yeah.
Okay.
I'll send you the PDF of this presentation. You can send it out to whoever.
Okay. And then on our next webinar, we will continue like the technology and innovative switches and controls. We've got building a sustainable future with affordable housing innovations. We've got Sean and Vanessa from Levin Electronics that will be here. So we'll talk more about lighting controls, HVAC controls, and the likes, just kind of as we talked about before in previous webinars. The code keeps changing and advancing to include more controls as we get through this for controlling energy use instead of just trying to get it more efficient, is to control the time it's being used. So here's my contact information. If you guys want to screenshot that, feel free to share that with anybody that might can use our help. And again, thanks, Juliana. Thanks, Gabe. I appreciate you guys' time. And we will see you guys on the next one.
Thank you, Randy.
Thank you.